So have you ever thought about that there are actually 4 pillars here to the web? So maybe 3 of them are quite well known. It's HTML, it's CSS, and it's JavaScript. But tonight we're going to be talking about the 4th pillar, which is WebAssembly. So in my presentation, I'm going to be describing here why you should actually consider WebAssembly in your next front-end project. My name is Håkan Silfvernagel. I work as a manager for AI and big data at Miles, a Norwegian consultancy company. And before we start here, I'm just going to go through a little bit of the agenda here for today. So first of all, we're going to cover what is WebAssembly. And then we're going to go through like a hello world example here, hello Wasp, hello WebAssembly. And then we're going to talk about how you actually want to do when you want to develop with WebAssembly. So what you want to do is you want to use a high-level language that you can compile down to WebAssembly. And because of that, we need to know about 1 or 2 high-level languages. So I'm going to give you an example here in Rust. So because of that, we need to have a quick introduction here to what Rust actually is. Then we will make a program here, a component in Rust. We will compile it down to WebAssembly, and then we will upload this WebAssembly to NPM. And then after that, we're going to start from scratch, write a web application, and then we're going to use this NPM package. So we're going to use Wasp in our WebAssembly. And when we're through with that, we're going to have a look at a little bit more involved example, a game of life example. And then we're going to cover a little bit about performance, because performance is a big deal here when we talk about WebAssembly. We're going to go through some real-world examples, go through the future plans for WebAssembly, and we're also going to cover some other frameworks that are using WebAssembly. Then we have a title here that might seem a little bit cryptic, that is says new old. You just have to wait to see what that actually covers. And then we finish off with some conclusions, and then I also have some references for you who want to have a little bit deeper look into this material. But before I start, I'm just going to say a couple of words here about me. So I work as a manager for AI and big data at Miles, a Norwegian consultancy company, and I'm quite active in the local user group community in Oslo. So I'm part of the Norwegian.net user group. I'm also part of the virtual group, the Azure user group Sweden, and I'm part of Oslo AI. I'm also running an online AI school called AI42. So if we have some time left at the end of the session, I'm going to be covering a little bit more about this online AI school. And if you want to reach me, you can find all of my links here on this slide. But let's start here with a background into WebAssembly. So in 2015, there was a group formed by all the major browser vendors, and by 2017, there was a WebAssembly released. And then by February 2018, a W3C public draft was published, and from December, this WebAssembly is a W3C recommendation. So that means that it stands on the same sort of standard as HTML, CSS, and JavaScript. And one of the great things here with WebAssembly is that it both works in all the major browser engines, both on desktop, but also on the mobile versions. So if we want to compare or contrast JavaScript with WebAssembly, we can see that JavaScript is, it's a high-level language, quite flexible and expressive, dynamically typed, you don't need to compile, and as we all know, it has a huge ecosystem that you can use. But on the other hand, WebAssembly is a low-level assembly-like language. And in a short while, we'll actually have a look at what it looks like. And it has a compact binary format, and what it promises us is that it promises a near-native performance. And you can write WebAssembly sort of from manually, but you don't really want to do that. And the reasons for that will be quite clear here in a short while. But instead, what you want to do is you want to use a high-level language like C or C++ or Rust or Go, or several other languages that you can compile down to WebAssembly. So this picture is trying to illustrate here that what you usually have is that you have a high-level language that you can translate. So the compilers will take this high-level language, and then it will translate it to an intermediate representation. As you can see here in this picture here, denoted by IR. And then you have another part of the compiler will compile it down to to the target architecture, which can be, for example, an x86 or an ARM processor. But when we talk about WebAssembly, we need to take into account that this is code that will actually be executed over the web. So we don't know beforehand what is this target architecture that will actually run on. So you can see WebAssembly sort of as a machine language for a conceptual machine. And you can also say that WebAssembly instructions are virtual instructions. So the browser will download the WebAssembly, and then it can compile it down to the target architecture that it's running on. And these two slides here are taken from a blog series by Lynn Clark that you can find here also, and that I recommend you to have a look at. So as I said there, WebAssembly is a new browser standard. It's based on a previous project called ASM.js, and it's an intermediate language. So in the same manner as you compile down Java down to bytecode or C# down to MSIL code. And it's strongly typed, and you have 32-bit integer, 64-bit integer, 32-bit float, and 64-bit float. So now we're going to be writing our first hello WebAssembly or hello Wasm. But as you saw here in my previous slide, we could see that we don't have strings and we don't have chars. So that means that it's quite complicated actually to write a hello world program in WebAssembly. So what you instead want to do when you write a hello world program in WebAssembly is you usually take the mathematical calculations like addition or subtraction. So that will be our hello world WebAssembly program. So in this example here, so there's a format called WAT, which stands for WebAssembly textual format. So here we define WebAssembly with, first we define a module, and then we define a function inside this module that we call add2. And this function has two input parameters, to 32-bit integer, and the result will also be a 32-bit integer. So WebAssembly is a stack-based language. You can pop and push on the stack. And then you can also use some 60 different mathematical operations here. So in this case, since we're using 32-bit integer, we used a 32-bit add operation. And then finally, we need to define what will this function actually be called. So if we have a calling program, that calling program can call the add2 because it's exported as add2. And in addition, we can also have, so WebAssembly has both a textual format and a binary format. And we can parse this WAT format, the textual format, and write it to a binary format. And you can see the result here on this screen here. So as we can see here, this is very much an assembly-like language. And if you want to use this, what you can do is you can write an HTML page where you fetch your WebAssembly, and then you read it into an array buffer. And then since WebAssembly is web standard, we can just simply call WebAssembly dot and then instantiate an object by this WebAssembly that we have just fetched. And then we can define an object that here we call it add2. So you can see here that we are using results instance exports and then the name of this module that we were exporting. And then we can use it just as any other type of JavaScript function. So if we alert this out on the console, then we'll have the result out here when we run it. Another tool that is worth mentioning here is something called the Wasp Code Explorer. So the Wasp Code Explorer, what you can do is you can load the binary WebAssembly module into WebAssembly Code Explorer, and then you can get the textual representation back. So that's what we've done here. So we took our WebAssembly module, we loaded it into this tool, and then we can see here in the textual format that it looks pretty much the same as what it did when we wrote our function. This can be a nice way of actually figuring out what does this WebAssembly actually do. So now when we covered our first WebAssembly example, we can see here that we didn't have many types. We had 4 different types. We don't have chars. We don't have no pointers. There's a lot of things that we don't really have. So we don't really want to work with WebAssembly in this way. So instead, the way that we want to work is we want to use a high-level language where we can express us much more freely, and then we want to compile down our high-level language into a WebAssembly. So one of these high-level languages is Rust. In order for us to understand this a little bit better, I'm going to be covering just a very quick introduction into Rust. Rust comes from Mozilla. It's a system program language. It has a syntax very similar to C or C++. It's strongly typed, and it compiles down to native code. And one of the design goals when they designed Rust as a program language was that it should be memory safe. That means that you don't have any dangling memory pointers or memory leaks. So when you use Rust, you should know about the Rust toolchain. The Rust toolchain consists of Rust app, which is an installer for Rust, and then Cargo, which is the Rust package manager. Cargo will upload your package into a site called crates.io, which is like the Rust community package registry. And here's an example of a hello world program in Rust. We just define a main function, we print out a hello world, and then we can use Rust compile, Rust to compile a Rust program. And on a Windows machine, it generates an exe file that we can execute, and we get hello world out on the console. But we can also use Cargo, so we can issue a command with Cargo new hello world, and it will create both hello world project here that contains of the main Rust file and also a Cargo toml file. So in the main Rust file, we get the function main, and then we can define what we want to do here in our main function. And the toml file is like a package definition of our Rust package here. So by minimum, it needs a name, a version, and also author. And if you have any dependencies, you also need to define that in your toml file. So we can run this by running cargo run. So cargo run, it will compile our Rust file, and then it will run the exe file that is getting generated. So some types here in Rust, we have both primitive types like integer and float, and we also have something they call primitive constructs, like that can be pointers or references or arrays. So now when we know a little bit more about Rust, now we can actually do what we want to set out to do here, which is we want to build a component in Rust. We want to compile it down to WebAssembly. We want to package this WebAssembly as a package that we can upload to NPM. And then after that, we want to, as any other web developer, we want to use this NPM package in our own application. So that's what we're going to have a look at here next. First thing, if we want to compile a Rust program to Wasp, first thing we want to do is we want to install this toolchain, the Rust app, the Cargo, and the Rust compiler. And then after that, we need to install an add-on called Wasp pack. So this Wasp pack will compile our code to WebAssembly. And we'll also install something called the Wasp bindgen. So the Wasp bindgen will generate some bindings, or I usually call it glue code. The glue code is JavaScript code that we can call from another program. And then this glue code will be responsible for making the calls down to WebAssembly. So here again is an example here of this package definition. So we have called our package Hello Wasp Silver, and we have an author, and we also have what type of library, what type of crate. So in this case, it needs to be defined as a cdilib. That's the type of crate that we're using here. And then we have a dependency here on the Wasp bindgen. So again, this Wasp bindgen is the code that is sort of responsible for the communication from the outside world down to WebAssembly. So I usually call it the glue code. And here we have the Rust file. So here we define that we are requiring an external crate, which is the Wasp bindgen. And then we also define that we need to use an external function, which is the regular alert function in JavaScript. And then we can define a function here, greet, which takes name as a string input parameter, and then we can just alert it out. Now we can use Wasp pack in order to build this to a package here. So then we get the package folder here with this content, and we will have a look at what this different file contains in a short while. But if you want to publish this to npm, you can just go into this directory and then do npm publish package. And then, as we can see here, we got the package published to npm that we call hello Wasp Silver. And we're going to be using that in a later example. But let's have a look at this package structure and what we get here from that. So first of all, we get the TypeScript file. And in this TypeScript file, it's defined what are the functions that an external application can actually call. And as we can see here, there's only one function, which is greet. And it takes an import parameter, which is a string, and it doesn't return anything. And then we also get the hello Wasp Silver JS. So this is this glue code I was talking about. So what this is, you can see that it says export function greet with an input parameter. And after a while, it calls the function pass string to Wasp. So that it tries to return wasp.greet with this input that it got. And then we also got the package.json, which is a regular JSON file here. And in order for us to use this in an example here, then we can write a webpack config file where we define an entry point to our application, index.js, and we write the package.json file. And in this JSON file, we write that we have a dependency on this npm package that we just created, this hello Wasp Silver. And in our index.html file, we refer to this index.js file. And in index.js file, we can import this hello Wasp Silver. And then we can call it asynchronously. So we can call a JS greet and then with some input parameters. So if we run this, we will get that back here on the console. Now we have seen some basic stuff for what you can do here with Rust and with WebAssembly. Now I'm going to show you a little bit more complex example here. This is an example that comes from the Rust Wasp, and it's the game of life. So the game of life is sort of a simulation where you have a couple of rules here. So one of the rules is that you have a simulation plan where you have live and dead cells, and then there are some rules on how a cell will live in the next simulation. So if you have a live cell with fewer than 2 live neighbors, it will die because of underpopulation. Or if you have a live cell with 2 or 3 live neighbors, it will live on to the next generation. And if you have a live cell with more than 3 live neighbors, it will die because of overpopulation. And then the last rule is if you have any dead cell with exactly 3 live neighbors, it will become a live cell through reproduction. And then if we run this thing here. So now we're running a simulation, and then we also have a pause button that we can push. And if we push this pause button, then we can go in. Now we pushed it, and now we can go into the simulation plan and add some new cells here and affect the simulation in one way or the other. Let's have a look at how this was built. So again, similar to our other previous examples here, we have a TOML file, which is this package definition. Define our package, our authors, what type it is. So similar to previously, it's a cdie-lib. And then if we have any dependencies. And again, we have this dependency on the Wasp bindgen, which is this glue file that I was talking about. And then we have our main Rust function here, we call lib.rs, where we define our simulation plan, or it's called universe here. So we define what is the width and what is the height of our universe. And then we also define some public getter and setter functions for getting the width and the height of the simulation, and also a toggle cell function that I was using, when we pushed pause, then we can use this toggle cell function in order to define a row and a column where we want to toggle the value of that particular cell. And then we also have this TypeScript file where it's defined what are different functions that a calling application, or which functions are available to the external world. So for example, we have the width and the height, the getter and the setters, and we also have this toggle cell function, which is also available for us to use. And then we have the JavaScript file, which is this glue file. So again, it tries to, for example, when we try to call toggle cell, You can see it tries to return was.universe toggle cell with some input parameters here. And if we want to use this, we can create an index.html file where we have a bootstrap JavaScript file, and in that file we are loading index. So this is the content here of our index JavaScript file. So here we import this universe, and as you can see here marked in red, we're calling this universe toggle cell with a row and a specific column index. So now I'm just going to take a little bit of water here. So now when we covered now we have a better idea here of what WebAssembly can be used for, we can talk a little bit more about performance. So in this slide, there are some people who have made some experiments running the same calculations both in JavaScript and in WebAssembly and on Chrome and Firefox and on Safari. And one of the things that we can see immediately here is that you get a much faster execution using WebAssembly, which is what WebAssembly is promising us. But another thing which is maybe even more interesting here to have a look at is that if you look at this box plot for the performance for JavaScript, you can see that the spread of this box plot is much, much higher for the JavaScript examples than what it is for the WebAssembly. So that means that if we write the program in WebAssembly, we can have a much higher confidence that this program will execute in a specified amount of time, and we can't really do that in JavaScript. So that can be a very interesting and important thing to take into consideration. And another thing which is also interesting to have a look here is that JavaScript has been around for quite a long time, so a lot of the browser engines has already been optimized for JavaScript, whereas with WebAssembly it's a much newer technology. So we can expect that this efficiency difference between WebAssembly and JavaScript will be even greater going forward. So then we have some examples here from the real world. So first I should mention here, so what are the real good use cases here for WebAssembly? So one of the good use cases here is you have an application that you want to run really fast. So think about if you have some mathematical calculations, maybe you have some simulation, maybe you have a game engine, or maybe you have a graphic engine or something along that way. That's a very good example for WebAssembly. And another good example is if you have like a legacy code base, or if you have a program that you already have developed, but that program is not available on the web. Maybe you have written it in C or C++, or it's in some technology that is not easily exposable on the web. Then you can write a thin wrapper layer using WebAssembly, and then you can run your application on the web, because if you can find language, so for example, if you have a C program, then C, you can compile that down to WebAssembly, and then you can use that in order to expose it on the web. And we're going to have a look at people who have done that in a short while here. But here in our first example, it's a digital signal processing library where they had an application here using both C and C++. And what they did was that they used WebAssembly in order to expose this on the web. And then it looks something like this. So this is for manipulating images and also live video. So you can see here that you can do different types of filters on this live video stream. And another example is from AutoCAD. So AutoCAD is a company that deals with drawings. So they have a large customer base. So they've been around since the 1970s. There are many different types of drawings that they want to be able to expose on the web. And until quite recently, they haven't been able to do that because this has just been available on the desktop. So the way that AutoCAD solved this using WebAssembly was that they were using a layer here with WebAssembly that could call down to the core C++ functionality on AutoCAD. And then you can use any type of modern UI component library like React or Angular or something. And this is also a good example of a separation of concerns here, because what you can do here is you can have your developers that have focused on the C++ code. They can still focus on their core competence, whereas you can have maybe other developers that are focused more on the UI and on the front end. They can use their strength, which is web programming. And the way that enables this is through WebAssembly. So WebAssembly is sort of a wrapper here between the new world, which is the web, and the old world, which is more this desktop application. So now when we covered sort of what is the current state, I'm going to be talking a little bit about what are the future plans here for WebAssembly. So one of the things that we can't do right now is we can't call directly to the DOM, or we can't call a web API, for example. And that's on the plans here for WebAssembly, that they want to be able to directly be affecting the DOM from WebAssembly. And also, maybe you saw here in most of my examples here, we needed to call, when we wanted to call our WebAssembly, we needed to do it in an asynchronously way here. But what they want to do is they want to be able to directly import WebAssembly right into JavaScript, so we can use it just as we are importing other libraries. One interesting thing here is something that calls Serverless Web Assembly. The WebAssembly is not only for the browser on the client, but you can also use it on the server. So for example, we have Cloudflare and also Fastly that supports WebAssembly on the server. And some reasons why you would want to do this is you want to have fast launch times. You might want to be able to not need to rewrite an existing application to JavaScript, but instead you want to be able to just compile it down to WebAssembly and run it on the server. And you get also more lightweight applications. So here you can see a couple of different scenarios here. So one is sort of a classical scenario where you have a server-side. So let's say that we have a calculation engine. So then we run our calculations on the server side, and the front end is just calling the backend to get the results. Or you can do everything here client side. You do your calculations in JavaScript on the client. Or let's say that you had your calculation engine in C, then you can compile your C code to WebAssembly, and then you can run that also on the client-side WebAssembly. Or you can run it serverless WebAssembly. So then again, you had your calculation engine in C, you compile it down to WebAssembly, and then you run it as a serverless WebAssembly. So some different alternatives here that we have for running this is either through Node as a serverless function. And with Node, it can also be interesting in what is sort of the penalty here in terms of initialization time here. With Node, we typically have somewhere around 200 millisecond startup time here. Then we have Fastly, has an environment they call the Fastly Terrarium. And here they have an engine called the Lucette engine. And with this, we get the initialization time down to 35 microseconds, which is a drastic performance boost from comparing to Node. Or we can use a Cloudflare worker. They are using the V8 engine, and here we get initialization times around 5 milliseconds. So you can see that there's quite a big spread here. So then you just have to see what would work out best for you. And as we have heard about here previously today, there's also something called the WebAssembly System Interface, or Wasp. So here the main idea here is that we want to have WebAssembly running outside of the browser. So in order to do that, we need some sort of an interface for an operating system so that you can call, for example, you can call the file system, or maybe you want to open a socket or something like this. So here's sort of, again here from Lynn Clark here, how this would work. So you have some sort of a guardian here that stands between the operating system and your WebAssembly. So the WebAssembly needs to request permissions from this guardian in order to do some sensitive operations, like, for example, a file read or a file write operation. And in general, WebAssembly is governed by the same rules as for JavaScript. So now I'm going to be talking a little bit about some other frameworks that are also using WebAssembly. So the first one is Pyodide. With Pyodide, we bring the Python runtime to the browser through WebAssembly. So that means that we as data scientists can again be using our NumPy, our Pandas, Matplotlib, and so on directly in the browser. So a good thing with this is that this makes it very easy for data scientists to share their results with other data scientists in a very easy way. And another example here is something called assembly script. So with assembly script, we have a subset here of TypeScript that has been compiled down to WebAssembly. And one of the things that you need to take into account here that, for example, Rust is based by Mozilla, but assembly script has a much smaller backup. So that can be interesting to know if you want to go here for assembly script or not. Another thing with assembly script you need to both allocate your memory, so you allocate your memory and then you do something with that memory, and then after that you need to remember to free up your memory again. And also, which has also been talked about earlier today here, is Blazor. So, by the way, has anyone of you in the audience used Blazor before? Oh, okay, so some people have used it. So basically there are two different flavors of Blazor. So Blazor is a framework which enables you as a developer to build web applications just using C#. You don't need to learn anything about JavaScript or anything about any new tooling. You can just use Visual Studio as you have been used to do before and write everything using C#. There are two flavors. Either you can run Blazor on the server. This is using a technology called SignalR to send events back and forth from the server to the client. Or you can run it on WebAssembly. The way that this works is that we have a version of the .NET framework that is running on WebAssembly. So by this, we can use any type of code that we can write here in .NET. We can actually have it running in the browser. So the history of this is there's a guy from Microsoft, Steve Sanderson, who is also here on this conference. So in the NDC Oslo 2017 conference, he presented WebAssembly. And he presented WebAssembly by making a quite simple example of how you can run a Fibonacci calculations in the web using WebAssembly. And this caught the interest from the Mono team at Microsoft. So they saw that Mono, which was an open source framework here of the .NET framework, can be a compile target for WebAssembly. And at the same time, there was a team in the ASP.NET team that were thinking of generating this Blazor framework. So that was sort of a good combination here. So the way that it basically works is you have your CS files, your CS HTML files, and then you compile it to .NET assemblies. Then since we have this version of the .NET framework, the Mono that can run inside the WebAssembly, we can actually run .NET DLLs inside the browser. So it can look something like this. So this is sort of the introductory example here that you have a Blazor app, you have with a counter, and then you can change some properties here on this counter. And then this is maybe the most interesting here, that here we are looking at what is loaded inside our browser. So for example, you can see our DLL, the Blazor app DLL, is running inside the browser. And you also have, for example, the MS Core lib DLL or the .NET standard DLL is also running inside the browser. We were not really used to see that before we were using Blazor. So Blazor is very interesting technology to have a look at. But for those amongst us that are more interested in functional programming, maybe we'll have a look at Bolero, which is a way that you can use F# in WebAssembly. So then you can develop SPA applications with the full power of F# and .NET. So I'm not going to say too much about this, but if you're a functional programmer or if you're a F# developer, I can highly recommend you to have a look at this Bolero framework. So now we've reached this cryptic headline called New Old. So the question here is, haven't we seen all of this before? So for those amongst us who has been around for a while. We remember the ActiveX component had the same similar type of promises as we have now with WebAssembly. We can remember Flash, or we can also remember the Microsoft Silverlight. So the question is, why? What does it make that WebAssembly should be more successful than all of these things? So I think one of the reasons is that now we actually have, because all of these previous examples, they have been proprietary standards. Now we have a web standard, which has been accepted by the W3C, and it's also seen as a pillar here of web development. So we have HTML, we have CSS, we have JavaScript, and then WebAssembly is sort of on the same level as these other technologies. So I think that is a good indication that WebAssembly will live much longer than these previous types of frameworks. So a question here, what is the conclusion? Should we go WebAssembly all the things? Because when I started looking into WebAssembly, there were many articles that said that now JavaScript is dead, WebAssembly will take over everything. But I don't think that's actually the case here. I think that WebAssembly is a tool that can be really useful in some very specific use cases. Like, for example, the ones that we talked about when you want to have high performance, maybe you have a mathematical engine or some graphical programming, or if you have some legacy code that you want to be able to expose out on the web, then WebAssembly is a very nice tool to have. But it's just one tool amongst many other in your toolbox. So I don't think there is any risk at all that JavaScript will disappear, either in the short run or in the long run. But you can see as WebAssembly is a very good tool to use for some specific use cases. Then I have some references. So you can there is both some references on the Mozilla webpage on WebAssembly, and if you want to know more about Blazor, or if you want to watch this presentation from the NDC Oslo presentation in 2017, you can find this on this link over here. So with that said, you can find me here either on my Twitter, which is Grevlis, or you can also send me an email if you should have any types of questions. So with that, I want to thank all of you for coming to my talk. Thank you so much. Yeah, sure.
What's the most complicated thing you've written in raw WebAssembly?
Raw WebAssembly, basically nothing. I mean, it's not an environment that you really want to do anything in, actually. It's more just for testing it out. And I think that's maybe one of the drawbacks right now with WebAssembly is that the tooling hasn't much to offer. So it's quite clunky to install, and you can get errors every now and then. But I think with time it will probably be much more improved. Yes, we have a question there. Yeah, so with near native, that's in comparison to a web application to, for example, C or C++. That's sort of the comparison here. No, we're comparing it to if you wouldn't run it on the web, if you would run it, natively just on your operating system without the web. Yes. Yeah. Yeah. Thank you. Yeah, then I just wish you a good conference. Thank you so much.